I hope you had a great lunch. So the final 3 talks of this wonderful workshop begin now. The first talk is by Flore Kunst on exceptional non-Hermitian topology.
Right, okay. So good afternoon, everyone. Welcome back from lunch. It seems not everyone has gotten back yet, but I will nevertheless start my talk already. So my name is Flore Kunst, as you can see here. So first of all, I'd like to thank the organizers for inviting me to this event. It's very nice to be here in the Alps. And I'm a research group leader at the Max Planck Institute for the Science of Light in Erlangen, so it's not very far away from Garching. And I'm going to talk about exceptional non-Hermitian topology. So why do we want to do something non-Hermitian, right? So when I talk about non-Hermiticity, I'm talking about the non-Hermiticity of operators. So you take some operator M and it's not equal to its adjoint. So why do we even care about this, right? Because I'm violating laws of quantum mechanics. I get complex eigenenergies, non-unitary time evolution, probabilities are not very well conserved. So the main motivation actually to look at these systems is that you can think of them as an effective approach to describe systems with dissipation. So if we actually take some random ordinary differential equation, where this psi is some n vector, and this m is some n by n matrix, then you actually find that this equation appears in many different places in physics. So for example, this describes Newton's equations for coupled oscillators, or Kirchhoff's law for linear elements. In photonic systems with classical linear waves, the evolution of modes is described by this system. So very explicitly, if you think of a photonic metamaterial, then the paraxial equation has this form. But also, of course, in quantum mechanics, we all know this as a Schrödinger equation for multi-level systems. And even if you think of open quantum systems, a Limblab master equation also has this generic form. So this equation has many applications in many different fields, and this is also why certain things in physics, for example, topological phases of matter, which are encoded in this M, and in a way also in the psi, can actually be observed in many different platforms, because it actually all comes down to this. So if we now make this M non-Hermitian, then this actually has applications in all these cases as well, because if you add friction in the case of your coupled oscillators, this M becomes non-Hermitian. If you add resistors or amplifiers in your circuits, then also your M there becomes non-Hermitian. Similarly, if you have photonic materials and you add gain and loss, again, you get a non-Hermitian M. So even in the Schrödinger equation setting, there are ways to get this to be non-Hermitian. One example would be, for example, if you include parity time symmetry in your systems. We'll get back to the symmetry in a few minutes. And in a way, of course, open quantum systems, this M or this IM, you would put them together, this would be a Liouvillean matrix. This is already inherently non-Hermitian due to the dissipation in your system. So this mostly focuses on classical systems, whereas here the applications are more in the quantum realm. Okay, so what I want to talk about, though, is non-Hermitian topology. So if we think of conventional topology, so Hermitian topology, then there's 2 things that I always think of. Yeah? So the first one is that you have robust boundary states. So you have a system in a topological phase. It has robust states on the boundary. You can see that in the spectrum under open boundary conditions. So this is for 2D Chern insulator. You take open boundary conditions in one direction. You still have periodicity in the other. You see these red bands appearing in the band gap. These correspond to chiral states that live on the edge of your cylinder in this case. The other component that you always think about is bulk boundary correspondence, which says that if you have a spectrum under open boundary conditions, this is more or less equal to the spectrum under periodic boundary conditions plus the boundary spectrum, and that you can define a topological invariant using your Bloch Hamiltonian, which actually says what happens if you have boundaries. Okay. So then a very natural question to ask is, if you want to do something non-Hermitian, what happens if my system is now non-Hermitian? And actually you find that next to these boundary states, there may be additional boundary states. These are called non-Hermitian skin states. These are basically bulk states, quote unquote, that pile up on the boundary of your system. Moreover, the conventional bulk boundary correspondence as it exists here, it can be broken. Yeah, so here I'm showing again a spectrum for a Chern insulator, but now I made a non-Hermitian Chern insulator. And the spectrum in orange is for the periodic case, whereas the spectrum in blue is for the open case. And you see this looks completely different. So the bulk boundary correspondence no longer holds. You can also see that a Chern number here completely fails to predict when chiral edge states exist. On top of that, you can have new types of degeneracies known as exceptional points, and that is actually what this talk will focus on. And as we will actually see, is that these exceptional points play a role in both of these phenomena as well. Okay, so what are exceptional points? So exceptional points are degeneracies in the spectrum at which the geometric multiplicity is smaller than the algebraic multiplicity. That means that your number of linearly independent eigenvectors is actually smaller than the number or the degree of degeneracy in your eigenvalues. Yeah, so your system becomes incomplete. So a minimal example would look like this. If you take this 2x2 system, the eigenvalues are simply given by plus minus the square root of alpha, and you have two eigenvectors, the right eigenvector and the left eigenvector. Yeah, where the left eigenvector you apply to the left of your matrix. So obviously this is Hermitian if alpha equals 1, and if we then actually make a plot of these eigenvectors, the right eigenvectors, you see indeed they're nicely orthogonal as they should be in Hermitian systems. Now, if we start to go away from this Hermitian limit, so we go between 1 and 0 for alpha, you actually see that these eigenvectors are no longer orthogonal. They're actually starting to move closer to each other. And when you're at alpha equals 0, only one eigenvector remains. Yeah, so this is when you are at the exceptional point. You can also see it here. Now your matrix assumes a Jordan normal form. Okay. So how do you get such exceptional points? Actually, the easiest way to think about it is if you just start off with a two-dimensional while node. So just a 2x2 system, kx sigma x, ky sigma y. You can gap this out. So this is also a bit of a sidetrack, but this is why Dirac cones in graphene are not so stable, because you can always add a mass term in the sigma z channel that opens a gap. But if I now instead add an I term, so I add an ibx sigma x, so I change this kx, it becomes complex, you see that this point actually splits up in exceptional points. Yeah, so this will be the real spectrum, the imaginary spectrum, and the absolute value. Okay. So then we can ask a question, okay, these exceptional points, they obviously exist in non-Hermitian systems, so how often do we actually encounter them, right? How common are they? And it turns out that for two bands in a non-Hermitian system to cross, you only need to satisfy two constraints. So it's quite easy to see, actually, again, if you think of a 2x2 system, two-level system, the sigma here is the vector polymatrices. This is a non-Hermitian H, so this D has a real and imaginary component. Then the eigenvalues are simply given by this equation. So to find exceptional points, you simply need to set this part, so the difference between the magnitudes to 0, and you need to set the real and imaginary part need to be orthogonal. Okay. This means that such exceptional points are extremely abundant in in non-Hermitian systems. Why am I saying that? It's because to find a two-level crossing in Hermitian systems, you actually have three constraints. And so these exceptional points are much more abundant than two-level degeneracies are in Hermitian systems. They have a few interesting properties also. So they are connected via what we call Fermi arcs. Yeah, so we have these two equations, which in a periodic parameter space, in a 2D periodic parameter space, I should say, you can solve them on some generic curve. So this black curve, on this black curve, you solve the magnitude condition, and on this green curve, you solve the orthogonality condition. So that when these curves overlap, you find the exceptional points here. Now, if you're on this green curve here, then you see this part in your eigenvalue equation goes away. So if you're then inside this gray region where the difference between these terms is negative, then your energies are entirely imaginary. So the real part of your eigenvalues disappears on this light green curve here. And this appears in the bulk spectrum of your system, and it's known as a Fermi arc. So this is an open Fermi structure in your spectrum. And you also have the complement in the imaginary part. Another interesting feature is that they're non-analytical. You can already see it a bit in the plot here. So if you actually perturb around an exceptional point, you find that it scales with the square root. So two-level degeneracies in Hermitian systems, they scale linearly, but these guys, they scale with the square root. So they're quite sensitive to perturbations. Okay. So we now have reviewed this case, but actually you can also have a different case, because what if I now add an I sigma z term, right? So I didn't have a sigma z here, now I add an imaginary sigma z. Then you actually see that the point, the while node, splits into an exceptional ring. And this, you can get this situation if you add symmetry into the game. So let's see how that works. So in general, so far I talked about two-level systems, but if you have an n-level system and you're looking for an exceptional point of order n, which means that you have an eigenvalue degeneracy of nth order, but also n eigenvectors coalesce onto 1, you need to satisfy 2n minus 1 real constraints. Sorry, this got moved apparently. So you can show that in general these constraints can be expressed into the determinants and the traces of your Hamiltonian. And again, in turn, you can express these guys into products and sums of the eigenvalues. So the constraints actually amount to setting these guys to 0. If you set them to 0, you will find an exceptional point. So what we can then use is that symmetries actually put constraints on their energy eigenvalues, which would then set some of these constraints to 0 automatically. So these are symmetries that do that for you, and you can see actually there are symmetries here that you might not be so familiar with from Hermitian systems. And that is the case because in non-Hermitian systems, you have many more symmetries available to you due to the fact that your Hamiltonian no longer equals its adjoint, which also means that the transpose no longer equals the complex conjugation. So these are the 6 symmetries that do this. So you have parity times symmetry, you have something called pseudo-Hermitian symmetry. This is a very new symmetry. Then something we call parity particle whole that has this form, chiral symmetry, pseudo-chiral symmetry, and sublattice symmetry, where you can also note that chiral symmetry and sublattice symmetry are the same symmetries for Hermitian systems, but here they're different, and you see they also lead to different constraints on the energy eigenvalues. Now, because this is what matters for us, it turns out you can just group these into 3 different groups to actually say, okay, what happens if I have symmetries in my system? And if you do that, you can see that the presence of these local symmetries reduces the number of constraints. So instead of having 2n minus 2 real constraints, you end up with n minus 1 and in some cases n. So if we now look at an example, so we look at pseudo-Hermitian symmetry or parity times symmetry, these are the 2 symmetries as described, and you again look at a 2-level system, you can show that this dot product immediately disappears. So in the presence of this symmetry, your eigenvalues actually simply read like this. As such, you would always find already an exceptional point in 1 dimensions and a ring in 2D, as we saw already sketched out before. It turns out, however, as my very clever PhD student Anton Montag figured out, is that you don't even need symmetries to reduce the codimension. You need only similarities. So here you again see the 6 symmetries that I talked about, but we already said we could group them into 3 groups based on their impact on the eigenvalues, but they actually all can be grouped into 3 similarities. So they have something called pseudo-hermiticity, where H is related to some H dagger via some psi, which just needs to be a Hermitian matrix. Then you have something we call chirality, although I think we're going to rename this, so this might change a little bit, where you have the same relation, but then with a minus sign, and something skew similarity, where H is related to minus H, also via some Hermitian matrix. And it turns out that just having these similarities in your system is enough to already stabilize these exceptional points in lower dimensions. Okay, so now I talked about exceptional points of order 2, I talked about the impact of symmetries, and I also mentioned quite a lot of properties attached to these EP2s. But actually, what are the properties of higher order exceptional points? And it might surprise you, but there's not a lot known in the field about this. So we decided to look at the simplest system after 2 bands, which is a 3-band system, to see what happens. So this is an example with pseudo-Hermitian symmetry, although this, as I just pointed out, also works with pseudo-hermiticity as a similarity. And this is an explicit example. So here what we're plotting is a 3-band model in 2D. You have a kx and ky parameter. I'm plotting the maximum of the difference between the eigenvalues. So this should go to 0, where all of them are the same, right? So indeed, here you find 2 of such points, and we say they're EP3s. And indeed, you can check this by looking at the inner product between the eigenvalues, which should be 1 at the exceptional points, because you just have 1 there. So how would you detect them? Oh, now it's actually working. Now the other guy isn't working. That's funny. Okay, so I tried it before, and then this video was working. Now this video is working, so it's a bit random. So the way to think about this, and I got these videos of my student Anton, is that if you actually, so here you have the EP3, if you move around the EP3, then you can actually see the eigenvalues dancing in a way. So what you can do is you can identify, oh, okay, now this stopped working, okay. An EP2 line, which connects them. So you can see that on this and this point, eigenvalues will coalesce either here or here. And you again have a Fermi arc where actually in this case, all 3 eigenvalues are going to be on the real axis. So why is this relevant? Because if you're actually doing an experiment and you're trying to detect these guys, it's going to be very hard because you need to actually be exactly at this point. So what this shows is that as long as you wind around one of these points, you will always see the same behavior, which you can see by looking how the eigenvalues evolve. So what we find is that in general, you can then for these symmetries make these kind of schematic diagrams. So what we find is they always appear in pairs, for example, EP3s in the presence of symmetries. They're connected via EP2 lines. You have some different kinds of Fermi arcs. And you can do the same also for the other symmetries. So parity-particle chiral symmetry, you have something very similar. And also pseudo-chiral and sublattice symmetry is a bit different because you basically have the situation from a 2-level system plus an added flat band. So everything just gets promoted to 3 levels. Okay, so how do you find them? So I talked a little bit about how you should observe them in the experiment, but actually to come up with toy models to find these points is not easy. So my student had quite a hard time to come up with good toy models for examples. So an obvious way actually to generate a higher order EP is to just write a Jordan block, right? So if you think in terms of hopping models, you just take a one-dimensional system. It has one side in the unit cell. So if you think of this as a hopping model, it's just one side in the unit cell, and you can only hop to the right. Very boring, if you will, right? This is actually known as unidirectional Hattano-Nelson model. And this just gives you an EP of order n, where the length of the chain is n. There's also a less obvious way to generate such higher order EPs in systems that are not necessarily the same size as the order of the EP. And you can do this in directed graphs. So if I take something similar, so I still have only one side in the unit cell, although here I suggestively colored the sides already because there's going to be some cyclic symmetry. And you say, okay, I can only hop one neighbor to the right, but 2 to the left. Then it turns out that this system has some 3-fold rotation symmetry. So that means if I add a 7th side, then the eigenvalue has to sit at 0 because of the symmetry imposed on the spectrum. That means that if I add another side, it again has to sit at 0, and you can actually prove that that is an exceptional point of order 2. You can also do this with more sides. So for example, if I now have a 4 coloring, so I go 1 to the right, 3 to the left, I get a 4-fold rotational symmetry. In this case, I have 6 sides, you get an EP2. I add another side, I actually get an EP3. So the point here is that these systems turn out to have a generalized chiral symmetry, which actually imposes a symmetry on the spectrum, which sets a rule for when EPs of certain order appear. So this is the rule. It's not so interesting, but it's basically related to the range of hoppings. And as a consequence of this symmetry, actually, the existence of these EPs is entirely robust against disorder in the hoppings. Yeah, so I didn't say what these hoppings are, but it actually doesn't matter. It just matters that they're connected with some way, with some strength. Okay, so why do we care about these points, right? So far, this has been a bit of a mathematics talk where I just talk about non-Hermitian matrices and look at the degeneracies and look at their properties. So you can actually find them in many experiments. First of all, the Fermi arcs I talked about, which in this case indicate to exceptional points of order 2, have been observed in a photonic metamaterial. So this is a system with gain and loss. Here you see the experiment, here you see the simulations. I'm sorry, I put the reference down here, which I think might be a bit hard to see, but in any case, they see very nicely these Fermi arcs appearing as predicted by the non-Hermitian theory. Then there are another experiment from 2017, they actually showed against sensitivity against small perturbations. So if you take a microring resonator and it operates at a so-called diabolic point, so this is actually what a sort of an ordinary degeneracy, if you will, you find a linear response against the perturbation. But if you now make this system a little bit lossy and you change the parameters in such a way that it actually operates at an exceptional point of order 2, you see that you get a square root scaling, and actually the response against a small perturbation is much more sensitive, which you can see in these transmissions over here, that for the exceptional point, this peak is almost twice the width. Here is another experiment where they showed unidirectional visibility in a Bragg scatter with PT symmetry. So this would be the Hermitian case, but if you then make a PT symmetric, you see, okay, the light goes through from the left, but if you go from the right, you actually see that it gets reflected. And on another note, in the theory work, we also predicted that if you take a quantum emitter and you couple it to a photonic bath that is lossy and it has exceptional points in it, you find non-algebraic decay in the emitter dynamics. Okay, so then a question you can ask is, what if a model has topological boundary states, right? So I started with topology, then I did a lot of talking about exceptional points, and I said it's actually related to some exotic phenomena. So let's actually look at this model again, where I said we have the unidirectional Hattano-Nelson model. Actually, if we look at the full Hattano-Nelson model, you also have hopping to the left. And this model actually exhibits something that we know as a non-Hermitian skin effect. Yeah, so as long as the magnitudes of these hoppings are different, all your states will pile up on the boundary. And this actually is related to a feature in your spectrum under periodic boundary conditions. So if you look at the Bloch spectrum here, which is very simple because it's just a one-band model, you see that it winds. So in the complex plane, it forms a loop. And it has been shown in these works here that if you have loops in your spectrum, that actually indicates a piling up of bulk states under open boundary conditions, which you can quantify by a spectral winding number. So if we think of an explicit example and say, okay, we now have a model which has the skin states but also has boundary states, what happens? So if we think of a 2x2 system, say the SSH model, yeah, so I just talked about one-band models, which are already interesting, but if we want to talk about topology in the sense of Hermitian systems, we do need to have 2 bands. So we just promote it, we go to 2 bands, we have an SSH model. It's not Hermitian in the sense that you have different magnitudes hopping inside the unit cell. Then you again see this phenomenon that we saw already in the start, is that the spectrum is very sensitive to boundary conditions. Yeah? So the orange spectrum under periodic boundary conditions differs from the open spectrum under open boundary conditions, where these red states are the zero energy states. You find a non-Hermitian skin effect, which is kind of obvious because of the different magnitudes, and extremely high order EPs. Yeah, so they sit here. So I already announced these EPs are actually related to this behavior, and that is exactly because in the extreme limit, where you can only go in one direction, you will find the EP. What is also quite interesting is that even though you see a skin effect, if you look at the inner product between the left and the right states, you actually find more bulk behavior again. Yeah, so this is called the biorthogonal product, where you actually look at left and right. You see the physics again starts to resemble how we know it from Hermitian systems. And topological invariants no longer predict boundary behavior. Yeah? So if you compute the winding number, you actually should find a zero energy state in these green regions, and you see that that's not exactly true. It's only in these much smaller regions. So your conventional bulk boundary correspondence is broken. So I just wanted to point that out to just let you know that these exceptional points, you can see them in experiment, but they also have physical consequences for topology in your systems. So you can remedy this situation of breaking the bulk boundary correspondence. I just want to tell you that this situation can be saved, and then we go to the conclusion. There are 2 methods out there. So either you can use something that's known as the non-Bloch bulk boundary correspondence, where you make your K parameter in your Bloch Hamiltonian complex. Then you can actually redefine your Hamiltonian as an H of beta, and then use that actually to compute your topological invariance. And the other approach is one that we launched, which is relying on this biorthogonal physics, where you actually have to look at inner products of your left and right states. Having said that, I'd like to summarize. So I hope that I've convinced you, by just giving you a small introduction into this field, that non-Hermitian topological phenomena are relevant and fascinating. We talked about exceptional points. I briefly touched upon the breakdown of the bulk boundary correspondence. If you're interested, I'd like to refer you to a review paper that we wrote on this topic. And of course, I would like to end by thanking my group members, in particular, Julius and Anton, who were involved in the work that I talked about here today. Thank you for your attention.
Thank you very much. Questions, please?
You were talking about properties of general non-Hermitian matrices.
Yeah.
So would some of these interesting exceptional points also show for unitary matrices?
No. No. So these exceptional points, they're truly non-Hermitian degeneracies. So they can really only appear in systems or in matrices that are non-Hermitian.
More questions?
Thank you for the very nice talk. I have a question. Something that I don't really understand is, like when you give the example that you call non-trivial of exceptional point of order n,
Yeah.
what is the meaning of the color again? I did not really get
Of the coloring, okay. Right. Sorry, this will take a few seconds. When I talked about
I think 20 slide, yeah.
this, right?
Yeah, exactly. Yeah.
The meaning of the coloring. Yeah, so basically, the coloring actually relates to something that I didn't talk about at all. So it finds its root in this rotational symmetry. But it turns out that for these models, you can actually write exact solutions for what is known as the Jordan chain. So at an exceptional point, your eigenbasis becomes incomplete, but you can write Jordan vectors or Jordan chain to complete your eigenbasis. And you can show that in the Jordan chain, so in this case you would have a Jordan chain of 2, here you would have one of 3, that these different states actually only live on these colored sublattices. So these colors actually relate to where the Jordan chains live, which actually also has another consequence, which means that for certain on-site disorder, this is also completely robust, the appearance of the EP. But that's what the coloring relates to. It's a bit technical, that's why I didn't say it. But I hope that helps a little bit. Yeah.
Thank you.
Hi. I wanted to ask, what is the underlying mathematical structure behind non-Hermitian topology? Because for Hermitian topology, I know that I have a G bundle over my Brillouin zone and so on. Yeah. So what's the one for non-Hermitian?
Yeah, it's a very good question. That is not so well known in that respect. Yeah, so I think to think of bundles in this case is going to be hard. So typically what people do, I mean, I guess, so what people usually do if you really say, okay, I want to check how my my topological model, how robust it is against some non-Hermitian terms, you take your Hermitian model that you know is going to be topological, you add some non-Hermitian perturbations, and then you see what happens. And then you can still compute invariance. You have to be a little bit careful because you now have right and left eigenstates, so there are multiple invariants you can do, etc. But this mathematical structure, I think, still requires some deeper thinking. Yeah.
Thank you.
Okay, I see no further questions, so let's thank the speaker again and move on to the next talk.